Hello, everyone. I'm Sue Tappan, a member of the SPARC Data and Resource Center. On behalf of SPARC and the Codeathon mentors and judges, I welcome you to the 2025 SPARC FAIR Codeathon winners announcement. This 3-day virtual Codeathon ran August 2nd through 4th and was made possible with funding from the National Institutes of Health. In its 5th consecutive year, the Codeathon invites teams from all around the world to come together to explore and build something new. SPARC has a lot of unique data, extensive access APIs, and powerful processing tools. Neuromodulation is an emerging therapeutic approach to treat diseases of the autonomic nervous system. Yet how to precisely control function while limiting undesired off-target effects is not well understood. The NIH SPARC program, which stands for Stimulating Peripheral Activity to Relieve Conditions, was initiated to bring together scientists studying molecular medicine, neuroscience, engineering, and computational science to develop devices to diagnose and treat diseases. The history of SPARC and the birth of bioelectronic medicine are explored in a recent MIT Technology Reports article. The precise neuromodulation would continue to be elusive without better understanding of how to bridge the body and the brain. As author Salim Adi describes it, the existing maps of the human peripheral nervous system were old and quite limited. Such a low-resolution roadmap wouldn't be sufficient to get the signal from the highway all the way to the destination. The SPARC program research initiative sought to address these knowledge gaps. Read the article identified here for the full story and visit the SPARC portal to see how the research community has risen to the task. SPARC connects the body and the brain with open resources that support research into systems physiology and neural control in the periphery. The SPARC portal is a trusted cloud-based platform for sharing multimodal data, meeting NIH, HEAL, and journal standards for scientific data repositories. SPARC is a growing ecosystem driven by leading scientists, accelerating research to advance basic science, clinical applications, and bioelectronic devices. The Codeathon participants had at their disposal over 350 curated datasets, models, and simulations from multiple organs, species, and research groups, as well as the robust data system architecture that includes a popular cloud-based computational platform, integrated anatomical maps powered by a knowledge base of neuronal connectivity, all created by the SPARC Data and Resource Center. 100% of it is available for reuse, and thanks to our recent acceptance into the AWS Open Data Partnership Program, all public data and models are stored and available for egress free of charge. The goal of the SPARC Codeathon is to use SPARC data and resources in novel ways, particularly in enhancing, demonstrating, or measuring fairness, findable, accessible, interoperable, and reusable. It aims specifically to encourage reuse of this rich scientific data. For longtime members of the SPARC team, it is exciting to see how people with fresh perspectives on the project and the platform want to use it to do real science. While our goal is to make that process ever more convenient, gaps and challenges exist. So the Codeathon was born. Each Codeathon project must demonstrate the value of SPARC's public data and/or directly integrate into or with any of the SPARC tools and resources to improve their existing capabilities. It is judged on the quality and completeness of code, documentation, and the recorded presentation that summarizes their project for the judging panel. We appreciate each individual who is willing to give up their weekend to live that in real time. The FAIR Codeathon is a global event, bringing people together from all sorts of global locations, including Bali, Austria, Ireland, Scotland, and New Zealand, to work together virtually for about 60 hours. As I said, it's made possible with support from the NIH SPARC Common Fund Program and the SPARC Data and Resource Center. The SPARC DRC will make all pipelines and scripts, software, and programs generated in this Codeathon available on a dedicated public GitHub organization and linked on the SPARC portal. Teams may choose to submit manuscripts describing the design and use of the software tools they created to an appropriate journal. Let's celebrate each team to see their project and solution before we reveal the outcomes of the judges' deliberations.
Good morning. We all know the SPARC portal is a goldmine of scientific data. But what happens when you take that data offline? It becomes a chaotic mess. Today, we introduce SPARChive, the tool that names your SPARC data, making it powerful and portable even without an internet connections. We are from Team A. I am Harris, the team lead of the team. I'm also the developer working on the full stack stuff. We have Akram, which is also the developer and working on the documentation. And also we have Mariam, who is also working as a developer as well as working with the documentations. For researchers working with SPARC data locally presents a real headache. You lose access the moment your Wi-Fi drops. Your downloads quickly become a scattered mess of folders and files, impossible to keep organized. Want to share a dataset with a colleague? Good luck. It's too big and complex. And exploring the data means juggling multiple applications just to preview different file types. These frictions slow down discovery. SPARChive solves this. It's an all-in-one desktop command center for your SPARC data. It's offline first, so your entire library is always available. It introduces the SPARChive format, packaging complex data set in a single shareable file, and it lets you explore with insight, turning your data from a black box into an open book. Let's take a quick look on functionality that SPARChive offers. First, you use the browser to search the entire SPARC portal. You can see now we found a data set of cancers. And to download the data, it's just very simple. You can just click the download and the SPARChive application will package it for you into a SPARChive file format. The data that you have downloaded will appear in the library, and here you can also upload your own SPARChive format, which means that the SPARChive format is very transferable. So for example, if you want to share data between your colleagues, you can just share the SPARChive data, and you can upload it to your own library to see it live. From here, we can open the data set, and also we can go through the file viewer. On the left, you see the entire file tree, which we can search. On the right, we can instantly preview any of the file that is being shown. So for example, you can preview the images, you can preview the CSV files, you can preview Excel files, JSON files, and we're planning to incorporate more file format in the future. With SPARChive as well, right now we're planning to integrate the signups. So instead of just looking from the data that we get from SPARC portal, the user can also generate some synthetic data. In this case, generating the synthetic EEG data. But SPARChive isn't just about convenience. It's about better science. It directly enhances the FAIR data principle, which is what this hackathon is about. SPARChive makes the data findable with its browser functionality. Accessible by being offline, and interoperable through the simple shareable SPARChive format. Most importantly, by solving this problem, it makes the data radically more reusable, either by you or by your colleagues. To get started with SPARChive is very simple. So we created a release note of our latest application. And because SPARChive is built in Electron, it makes it multi-platform. So it's not only available for MacBook or for macOS system, but it can also available for Windows system. But at the moment, because of the limitation of the time of the hackathon, we can only generate the application for the macOS. For SPARChive, we have so much idea that we want to build upon, but because of the limitation of the time, as I said previously, we cannot do it. So for example, we want to build SPARChive for other platforms as well. We want to add more advanced search filter, we want to add dataset versioning, and also we want to expand on what kind of file the user will be able to preview. With this, we want to acknowledge the mentors that has been very helpful throughout the hackathon, the open source community, and the flat icon creator, because we've been using it a lot for our SPARC applications. Thank you very much.
SPARC successfully combined practical utility with technical innovation, creating a solid foundation for offline SPARC data management that could evolve into a more comprehensive research platform. The judges appreciated the well-structured, usable project with clear technology stack and alignment with FAIR data principles. The app has a clean UI with multiple installation methods to accommodate different user preferences for offline SPARC data access. Well done, SPARC.
Hi, and welcome to our pitch on SPARC Fuse, one data format to unite them all. Initially, we planned to work on a data-driven time series forecasting project. However, during the preparation stage, we faced a huge issue in terms of FAIR principles when it comes to working with SPARC datasets. For this reason, we switched the focus of our project a bit. So what's the problem that we've been facing? Currently, SPARC hosts more than 40 fragmented file formats with countless of subvariants in terms of internal file structure. As a result, researchers waste hours on converters and in writing loop code instead of analysis. The inconsistencies in formats break accessibility, reproducibility, and interoperability, and ultimately block cloud workflows. We strongly believe that FAIR data isn't really fair if it can't be screened at scale. So here's the solution. We developed SPARC Fuse, which is a tool that automatically remaps any supported file into a uniform chunked SAR store, or optionally also .mat or .npc for legacy workflows. Currently, we support out of the box more than 80% of imaging and time series formats that we can find on SPARC, and we verified that across 38 different SPARC datasets. Why does it matter? With SPARC Fuse, we can cut the time needed to load a dataset from hours to a couple of seconds. That means that researchers can really spend the time on the science and not on data format wrangling. Also, we enforce interoperability out of the box. That means we have a unified file layout and researchers know what to expect to find in the file, and also they can use a single loader for any SPARC data. SPARC Fuse also provides cloud-ready chunks. By using SAR, we enable scalable streaming analysis on high-performance computing clusters and S3. Through all that, we boost FAIR principles because data becomes instantly accessible, interoperable, and reusable. Also, don't worry about metadata. It's always included. We include all SPARC metadata from subject ID to modality directly into the file, so it doesn't ship as a sidecar. We also add conversion-related metadata, such as source format, sampling rate, and mapping approach, you name it. All in all, we provide a self-describing output that is ready for analysis or publication. Now, how does it work? We use smart mapping with confidence scoring. That means we got handcrafted, expert-written mapping descriptors for common formats used in biomedical research, in particular in neural engineering. If there is no descriptor available, we use auto-mapping fallback. That means we score all descriptors and pick the best match for the file at hand. And don't worry, everything is transparent. That means that all mapping scores and methods used for the conversion are logged into the metadata. All right, how can you use SPARC Fuse? There are different options. The first option would be to use the command line interface or the Python API, which allows you to convert single files or entire SPARC databases with one function call. We also created a browser extension that adds a convert and download button to every dataset page on the SPARC portal. With that, the user can convert and download single files and even entire SPARC databases with one click. SPARC Fuse creates cloud-first outputs. That means you can stream SAR directly from S3 for zero-copy workflows on laptops, high-performance computing clusters, or Lambda. Overall, SPARC Fuse allows researchers to focus on science by skipping converters and proprietary formats and go straight to analysis. Finally, why SAR? SAR is a chunk storage format. That means that data is split into tiny, independently readable and writable tiles. It's highly optimized for cloud use. That means the chunks live as S3 objects and you can stream just the bytes that you need. SPARC Fuse together with SAR is fully parallel ready. That means you can use tools like Dask, Ray, or SPARC to slurp chunks in parallel for speed. To benchmark that, we decided to compare the time needed to load 100,000 sample slice using SPARC Fuse with S3 support compared to a SPARC download and slice. We could obtain 100,000 samples in just 300 milliseconds using SPARC Fuse with S3, which is 33 times faster than when using a direct SPARC download. Finally, SAR is based on OpenStack. It's community-driven, language agnostic, and adopted by many institutions like NASA, UME, SAR, and others. With that said, I'm wrapping up already. I would like to thank my amazing team, which made this project happen in just under 2.5 days of Codeathon. And we are really looking forward to seeing the community put it to use. Thank you very much.
Thank you, SPARC Fuse. SPARC Fuse transforms data accessibility across the SPARC ecosystem, making complex format conversions invisible to researchers while dramatically improving performance and enabling new research possibilities. The judges applaud your creative behind-the-scenes approach that seamlessly integrates into existing workflows. By creating a unified solution handling 40+ file formats, which are present in over 80% of SPARC datasets, SPARC Fuse was seen as having strong FAIR compliance that could remove critical research barriers to cross-dataset analysis and comparison. The project enhances all FAIR dimensions through format standardization and cloud accessibility, according to the judges. Clean, accessible workflow with thorough documentation of data transformations. The documentation was stellar. All told, SPARC Fuse seems poised to tackle the eye of FAIR interoperability head on. Well done. The third Codeathon team created SPARC Plugins.
The SPARC project provides well-curated datasets and knowledge bases for advancing bioelectronic medicine. The SPARC project also provides web tools for exploring these resources. This includes viewers and different maps to explore connectivity, for example, anatomical connectivity. However, the problem we have is that the SPARC portal lacks the ability to easily integrate new features. So here are examples, some of these new features that are quite difficult to easily integrate. These include being able to perform customized searches across different data sets, being able to modify and extend existing functionality, such as those of the viewers, being able to add new interactive features, for example, the ability to annotate medical images, having chatbots, for example, and also it's challenging for non-technical users to be able to interact with building such new features. Furthermore, there's also a limitation in that most of these capabilities provided by the SPARC portal cannot really be used while these models and the data sets are being developed. So also another challenge is implementing such capabilities is a significant overhead for the SPARC community. So our solution is SPARC Plugins, a framework for dynamically integrating rich interactive web apps into the SPARC portal in accordance with FAIR principles. We provide the ability to build these plugins that can access SPARC resources, reuse and extend existing SPARC viewers, link to all SPARC computational services, integrate rich interactive features, such as the ones I mentioned earlier, and much, much more. So what we've done is we created a modified version of the SPARC portal. And on that portal, we have a new dedicated plugins page where users can browse and activate plugins. Here is some examples of the plugins we created. We created the standard Hello World plugin. We've created a plugin that shows how we can extend the simulation viewer. And we've also created an AI chatbot, a plugin that can allow us to search data sets. And finally, we created a plugin that shows how you can view and annotate medical images. Here we use the NN Interactive state-of-the-art AI model, which has been pre-trained on 65,000 images from across 120 public data sets around the world. So this shows the power of how we can build these plugins. And these plugins are dynamically integrated into the portal without needing to, without needing to add any more code to the portal itself. We've also provided a cloud-based plugin development environment directly within the portal. This allows you to register new plugins, automatically build them, and test them all within the SPARC portal, and also submit them for review by the SPARC development team. We've also added generative AI support, which allows building and integrating plugins directly from a prompt. And this is also directly on the SPARC portal. So this enables non-technical users to rapidly prototype plugins for their needs. We've also provided a local plugin development environment, which is easy to set up and container-based, which deploys a local version of the SPARC portal. And this can load locally stored datasets. So here's an example of it being used for annotating MRI images that are used for diagnosing breast cancer. So we've provided tutorials that show how you can build these plugins. Now, in terms of our impact, SPARC Plugins promotes reuse of existing SPARC resources. It enables users to easily add new features dynamically into the SPARC portal. It empowers non-technical users to contribute and build tools that are catered for their needs. And it also reduces the reliance on core engineering teams, and by enabling broader participation and enabling faster development. So that because it's built on FAIR standards, it will enable SPARC resources to be integrated into other portals and platforms being developed around the world. So I'd like to thank the SPARC program and our Codeathon members. Thank you.
SPARC Plugins is envisioned to transform the SPARC portal from a static platform into dynamic, community-driven ecosystem that evolves with researcher needs while maintaining system integrity. With strong technical architecture and exceptional educational documentation, including 5 tutorials, SPARC Plugins creates a live test system that enables hands-on learning and experimentations. The judges were enthusiastic about how the team democratizes portal enhancement, bringing a strong community element to allow users to create tools for their specific research needs. Rapid adaptation to emerging technologies and user needs definitely sounds like a key community wish list item. So we are thrilled to see your exploration in this area. Nice job, team.
All right, I'm going to try and speak slowly with my New Zealand accent. However, at Toxic Trace, we've been busily mapping end-to-end how toxins that are aware and available in our everyday lives are affecting the nerves inside of our body and potentially compromising what SPARC is trying to achieve. If we share one case study around the formation of PFAS and how one company secretly poisoned the planet. Now, we're all a fan of Teflon and non-stick frying pans, but what this unpacked was a global disaster in terms of forever chemicals which are existing in our bodies, and we don't know how they are affecting us. And as they come under regulatory pressure, we are finding that they are changing the compounds and the molecules to potentially worse compounds. Now, if we look at the presence of these forever chemicals around the world, in the top right, we've got America, where there are known sites all around America. Bottom left, we've got a map of Europe. Now, in this case, dots are not good, and the whole area is basically covered in them. And we've also got data down under in Australia. These are all links which we can click through to those maps. So the system of regulating chemicals is broken. The impacts on our nervous system are unknown, especially the cumulative load, which brings a huge uncertainty to scientific studies. And that's what we're trying to trace. We've considered a range of stakeholders, right through from public sector guardians and regulations, through to platforms like SPARC with academia and research, right down to the consumer and the end user. Now, if we can connect with those consumers and elevate their awareness of what's happening typically behind closed doors and bring up their level of understanding, customers can vote with their wallet and their money to enforce a better, truer system. And we've got growing consumer interest in this. In the top right-hand corner is an image depicting a teaspoon of microplastics in our brain. And what we set out to determine was how impactful some of these are. But as you can see, typically there are buzzwords on the internet which fly around. Per and polyfluoroalkyl substances, such as PFAS, have been spiking more recently. Back in 2020s, BPA was the topic of discussion, and microplastics have been, consistent sort of in the middle of those trends. So if we look at the typical concentrations or amounts that particularly babies, pregnant mothers, and typical adults are consuming, it can be quite alarming in terms of BPA, PFAS, and phthalates as 3 potential toxins. Now, what we've got here is in the second row is the weekly consumption based on typical food consumption in New Zealand and the potential loading of these toxins in the food, and then annualizing that number. And what we're uncertain is, what is this impact having on us in 2 years, 5 years, 10 years, our lifetime, as these plastics become more prevalent? So to unpack this, Toxic Trace built out a range of features into the SPARC platform, starting off with a health quiz, helping people to detox and connect with medical device companies, understanding how these molecules actually are interacting, and a way for consumers to get engaged with the research to bring in new funding models to enable cutting-edge research to continue. Now, we couldn't quite recreate the SPARC human body with the SVGs that was clickable, so we ended up with our cartoon SVG, which is all clickable. And once you've completed your health assessment quiz, which is a simple range of 7 questions to start with, we end up with health scores on each of our main body organs, such as our brain, our lungs, our heart, our liver, etc. And we're looking into things like how many plastic takeaway containers do they consume, what is the types of diet, and this gives a percentage score through to the health of those organs where plastics can be accumulated. Each of these organs has a Wikipedia page where you can click in and learn how, for example, on this slide, we're looking at BPA impacts the human brain. We also provide detox plans. So what are the ways to get PFAS out of your body? Now, the scientific evidence shows that this is very persistent, limited natural elimination, and we've got studies to support this with a clickable link. Now, there are detox strategies such as probiotics, beta-glucans, saunas, liver enzyme boosters. But what we're seeing is medical device companies exploring things like blood filtration. And even people like Orlando Bloom in June this year spent over $10,000 on blood filtering procedures to remove microplastics from his body because we're unsure what these implications are going to do. So what we set out to do was, how do we use these tools to help medical device companies establish better links with consumers and help them fund their development? To do this, we've started unpacking a lot of the misconceptions with what does microplastic in our brain mean, or where else does this impact our human body? So in our structure viewer, we can see in the blue ribbon structure our estrogen receptor. And inside of it, we've got an estradiol ligand, which is basically the molecule, and we've got our toxin ligand, which is essentially BPA in this case. Now, it seems scary. These compounds line up, they're blocking the estrogen receptor, but what we see is through molecular dynamics and the research is that the BPA binds around 6,000 times weaker than the estrogen. So there should be less of a concern around this particular interaction. In our support research view, we allow people to subscribe to the latest up-to-date research and potentially sponsor tests specifically into certain food items, whilst publishing all of this data to the wider public following FAIR principles. And if we look at a very simple and very optimistic projection, if we've got a global population of 7 billion people, and we were able to get interest from 0.1% of the global population, and they were to contribute $100, that would unlock $700 million of funding, right? We know these numbers are construed, but if we think about the research that we need to develop, how do we attract the appropriate sums of money to get this attraction? Now, we've also got a sidebar, which helps us understand further the particular toxins, the interactions that they have, and also how this impacts the nerves. So we've currently built out 4 toxin cards, such as BPA, and we basically unpack a lot of the affected systems in our body, such as the endocrine system, the reproductive system, the cardiovascular system, the common sources where you can get this plastic into your body, linked again to research papers and additional information. We've taken this further and mapped 11 interactions where we are confident in the comparison between natural ligands, what our body should expect in these receptors, and the toxin complexes, which is sometimes interfering inside our body's cells. Again, we're rating the evidence level on this, and we're building out these 3D models that people can view in more data. And then we also bring this back to how does this affect the nerves, right? What SPARC is predicated and built around. So how does the BPA in the estrogen receptor impact the vagus nerve? Now, this is a lot of really complicated science that we're only able to scratch the surface on, and we would like to delve deeper into these impacts. But we are able to see and link how these toxins that are in people are starting to affect nerve function. So we've got blunted vagal tone, higher systemic inflation, greater metabolic syndrome, and basically we're disrupting the gut, brain, pancreas signaling according to the research. Now, to help modern consumers unpack and understand all of this data, we've also introduced True, which aims to be our source of truth from all of our data, which essentially is a AI-enhanced chatbot to help people understand all of this. And where we're trying to build towards is a project we called STEM Assist, right? So if we can help medical device companies to understand how to better filter and monitor and manage all of these toxins and potentially bring new customers to them to help detoxify their systems, STEM Assist is trying to also work within the SPARC program to be able to potentially stimulate, say, the vagus nerve to enhance the liver functionality to be able to process these toxins itself before, after, or during these processing treatments. And that is a wrap from the Toxic Trace team from New Zealand and a few Kiwis based in Bali. Thank you very much, and we look forward to the judging session.
Thank you. Our fourth Codeathon team presented us with ToxTrace, a functional application that successfully translates complex molecular interactions into accessible educational tools, making toxin research more understandable for public health awareness, utilizing the SPARC MAPS framework. The team created a thorough and easy-to-follow user walkthrough with good general technology descriptions and installation instructions. The educational content was well presented with helpful screenshots and clear feature explanations accessible to the general audience. The judges were intrigued by the focused scope and clear feature set that brings a new dimension to the SPARC portal, an innovative take on SPARC's motto of bridging the body and the brain. Our last team is SPARCats.
This presentation by SPARCats, Augmenting Data for AI. The SPARC Consortium unites researchers from over 60 research groups with the goal of deepening understanding of the autonomic and peripheral nervous systems to understand how bioelectronic interventions might enable new and effective treatments. As they investigate the autonomic and peripheral nervous system, they often want to apply AI tools to analyze data and to quickly derive answers to scientific questions and address medical needs. While the power of AI tools is readily recognized today, it is not so easily achieved. This is due to a range of factors, including the technical barriers to develop and implement an AI project and the demand for quality, relevant data. Good data can be hard to find and is expensive to collect. Researchers need a tool to seamlessly discover and augment publicly available data for AI training. Enter the SPARC Augmented Time Series Toolkit, SPARCats, allowing seamless AI discovery within o²SPARC. Tools are offered as cookie-cutter services that bring together data search and augmentation within o²SPARC. Alongside, we provide tutorials that make it easy to adapt these tools for your own AI workflow. SPARCats was developed with fairness in mind. The search tool enables users to easily find similar data. The Augment tool enables users to reuse existing data to effectively train AI tools. All of the modules are offered within o²SPARC as cookie-cutter services that are easy to use or adapt into your own custom workflow. We think that these tools will be useful more generally in a wider range of workflows, particularly the ability to search the SPARC data portal for data directly within o²SPARC. Let's explore how a researcher might use SPARCats to evaluate the effectiveness of their vagal stimulation experiment on cardiac data from a rat. They want to use AI to compare it to published control data. First, they search for similar published data to bolster their training dataset. This can also be to act as a control case for their intervention. The search feature can be reused in any o²SPARC workflow in order to identify and collect data from the SPARC portal. Next, they augment the data that they have collected. The augmentation is configurable, and the service comes pre-configured with some defaults. With the augmented data, they are now empowered to train an AI tool with a convenient pre-processing data service that takes care of test-train data splitting. We have also developed a series of tutorials to cover use cases from basic setup for non-coders to developing workflows for augmenting existing data that you have collected yourself or public data that you collect from the SPARC portal. We also include a tutorial on deploying a pre-trained model as well as transfer learning. SPARCats accelerates data discovery for AI and brings breakthroughs in the laboratory into healthcare. SPARCats generates synthetic, augmented physiological data from data available through the SPARC data portal in order to improve AI training. It is available as modular tools within the o²S²PARC platform. On behalf of the SPARCats team, thank you.
They've gotten together to address real data discovery and machine learning training data scarcity challenges. That's Team SPARCats. The judges appreciated the innovative synthetic data generation approach and that time series augmentation features to address real machine learning training challenges. The integration of AI tools across the SPARC portal enables easy dataset searching, configurable data augmentation through time warping, and synthetic dataset creation. The enhanced search functionality combined with the hands-on tutorial notebooks provide clear benefits for researchers working with limited datasets. The seamless integration with the o²S²PARC platform was particularly lovely to see. Stellar job, team. Last but not least is the team who brings us QSpark.
We've developed QSpark, a natural language chatbot that helps researchers explore SPARC's high-level connectivity data through intuitive conversation-style queries. SPARC is an NHI Common Fund program which aims to map how electrical signals control organ functions, supporting treatments for conditions like hypertension and heart failure. To do this, SPARC has gathered extensive data from over 60 research groups covering thousands of subjects, species, and anatomical structures. A central resource is SCAN, the SPARC Connectivity Knowledge Base, which captures how parts of the nervous system are connected. An earlier tool, the SCAN Natural Language Interface, lets users query this data using natural language and ChatGPT. QSpark builds on this foundation with improved performance, interactivity, and visualization, making it easier for researchers to ask questions, explore connections, and view results with anatomical context. The problem: while the original NLI is useful, it does have a few limitations that affect the user's experience. It requires users to write precise domain-specific queries, which can be difficult for non-experts. It's a single-turn tool, so it doesn't remember your previous questions, and there's no real conversational memory. The response time is also heavily dependent on OpenAI's latency, and it accounts for 95% of the current wait time. And currently, it can't integrate with FlatMap, which limits anatomical visualization. Finally, the interface doesn't support chat history, which can make interactions feel a bit disjoint. So overall, it's a powerful tool, but it's not particularly approachable or interactive. And that can create friction for researchers trying to explore the data. Our solution is QSpark, short for QuestionSpark. It's a conversational chatbot that supports multi-turn dialogue, meaning users can follow up questions and build upon previous answers. We focus on a few key improvements: faster access, whether running locally or in the cloud, a modular architecture aligned with FAIR data principles, open format support so it's easy to use and extend, and most importantly, flat map integration so users can see anatomical visualizations alongside their query results. This makes QSpark more usable, more interactive, and better suited for a range of research tasks. We've also developed a short tutorial walkthrough on how QSpark works. First, we show how to deploy the QSpark language model and run a basic query. Then we connect it to the scan dataset so it can provide expert-level responses with relevant metadata. Through a simple web interface, users can ask questions and get both structured and unstructured outputs. We have a tutorial that shows you how to interact with this web-based UI. And finally, we show how the system integrates with FlatMap to produce anatomical visualizations from the results. Each part of the tutorial is designed to be clear, practical, and easy to follow. In terms of impact, QSpark improves how researchers interact with scanned data, making it more findable through smart search, metadata tagging, and semantic ranking, accessible with intuitive interface and support for local or cloud-based use, interoperable thanks to the open data format and API, integrated with FlatMap, and reusable with documents and tutorials to help other teams adopt and extend it. By making the data more approachable, we've helped to increase its scientific value and broaden its reach. Finally, we'd like to thank the SPARC program and the mentors from SPARC Codeathon who supported us throughout this project. That's QSpark. Thanks for listening.
So before this video, I thought perhaps that QSpark was a nod to James Bond's top secret technology guru. I now know it stands for question, but even if QSpark didn't bring in James Bond into the picture, I think it's apt. The project presents an excellent and creative idea to address usability barriers for complex platforms like SCAN. Judges praised the novel application of conversational AI to scan data exploration with local LLM development and RAG implementation with conversation memory. The use of AI to help navigate and answer questions about flat maps with visual representations is innovative and hadn't been attempted before. This team focuses on a resource that is near and dear to my heart, working to make access to SPARC's anatomical knowledge more accessible. I enjoyed your approach and applaud how you make SPARC knowledge more searchable and visually interpretable. Spectacular job, Team G. And so now it's time to announce the winners. Before we do that, I'd like to take a moment to thank our judges who set aside time from their busy schedules to support our open science mission through the Codeathon. Yvette Wharton and Laura Armstrong are from the University of Auckland. Salman Faris comes to us from the Open Source Hardware Association, where he is a member. Caitlin Melora, Rebecca Black, and Joseph Monaco are all from the NIH. And a big shout out to them for pulling together their thoughts for each team and establishing the criteria for the discrimination between the projects. Thank you so much. So now for the winners. Third prize goes to SPARCats. It's an o²SPARC tool to accelerate data discovery by AI and bring breakthroughs into the laboratory. Bring breakthroughs in the laboratory into healthcare. Congratulations, SPARCats. You guys did great. Second place goes to SPARC Fuse, the file unification and standardization engine for SPARC datasets. Congratulations, team. You did a great job. Our grand prize winner is SPARC Plugins, a framework for dynamically integrating rich, interactive web apps into the SPARC portal in accordance with FAIR principles. Excellent job, team. You guys really brought a community focus to the Codeathon project, and the judges really thought that that was spectacular. Excellent job. And congratulations to every participant in the SPARC Codeathon. We really appreciate you spending about 60 hours working together on novel access points to SPARC data and SPARC resources. We really appreciate it. So congratulations to all teams. Our grand prize winner is SPARC Plugins. Second prize goes to SPARC Fuse. And our third prize goes to SPARCats. If you like what you've seen today, before we close, I invite you to become a member of the SPARC community, to find, use, and share models, data, and resources about the peripheral nervous system on the SPARC portal. Thank you for helping broaden our collective view of SPARC and giving us a glimpse of the different ways the research community will use our shared platform in the future. Thanks, everybody.